In the spring of 1953, tests conducted at the Nevada Proving Ground sent shockwaves through the Soviet Union. The United States had successfully tested the T-131, an 11-inch atomic cannon, better known as Atomic Annie. The weapon fired a nuclear projectile a distance of 17 miles. This event was seen as a display of strategic superiority, a direct challenge to the socialist bloc. Soviet leadership analyzed the implications of this technical achievement. The enemy's possession of tactical nuclear weapons capable of inflicting critical damage on large troop formations had shifted the balance of power. The USSR decided to take countermeasures to restore parity in this global standoff. On November 18, 1955, the USSR Council of Ministers issued a secret decree that launched a massive overhaul of Soviet artillery development. Two major defense contractors, the Kirov plant in Leningrad and the Kolomna Machine Building Bureau, were tasked with developing two types of super-heavy nuclear artillery. The first project was the 16-inch self-propelled gun 2A3, the condensator 2P. The second was the 16.5-inch self-propelled mortar 2B1. The latter was named the Oka, after the river which is a tributary of the Volga. The engineers faced a complex technical challenge: create a mobile weapon capable of delivering nuclear warheads tens of miles away. Boris Shavilin, a specialist who had previously worked on rocket artillery systems, was appointed chief designer of the mortar. Project leaders knew the Americans were already 2 years ahead in this field. They needed to close that gap on a tight timeline, while also demonstrating the high level of Soviet engineering. The work was divided up. The Kolomna Bureau was responsible for the artillery component, while specialists at the Kirov plant began designing the chassis. The T-10M heavy tank served as the foundation. However, even its chassis needed substantial reworking. Since the unit's calculated weight exceeded 55 tons, and the powerful recoil demanded highly durable components, the design was modernized. Engineers reinforced the torsion bars, installed 8 pairs of road wheels on each side instead of the standard 7, and added 4 return rollers. The tracks were widened to better distribute the weight across the ground. The key element of the project became the 66-foot barrel. The 16.5-inch gun had a length of 47.5 calibers, which was necessary to ensure maximum firing range. Production was handled by the Barricade plant in Stalingrad, which have extensive experience in manufacturing artillery systems. Factory workers received blueprints for an artillery system that boasted design features truly unique for the time. At the same time, specialized ammunition was under development. The projectile was codenamed Transformer and was designed based on the nuclear warhead of the RDS-9 torpedo. The Finn's shell weighed 1,477 pounds, while the yield varied between 13 and 25 kilotons. The technical specs of the munition meant it could wipe out a town or a large troop formation with a single shot. The calculated range for standard shells was 16 miles, while rocket-assisted projectiles increased the distance to 31 miles. For comparison, the American M65 Atomic Annie had a range of 17 miles. By 1957, the production process at 2 facilities was complete. The first prototype of the mortar, given the factory index Object 273, was ready for testing. Weighing 61 tons and made of steel, aluminum, and special alloys, the structure sat in the assembly hall of the Kirov plant. The unit stood 19 feet tall, and with the barrel lowered, it was over 66 feet long. A 750 horsepower V12-6B diesel engine was designed to give the vehicle a top speed of 19 miles per hour on the highway. The design of this artillery unit had a distinct technical feature that set it apart from most systems of that era. The mortar completely lacked recoil mechanisms, because creating hydraulics capable of dampening the recoil energy from a 16.5-inch shell proved to be too technically difficult. An alternative engineering solution was applied. The recoil was absorbed by the entire tracked vehicle moving backward. To handle this, the chassis was equipped with special reinforced hydraulic shock absorbers and lowering idler wheels that dug into the ground for extra support in the firing position. The crew cabin was located at the front of the hull and spanned its entire width. This structural design distinguished it from the condensator-type unit, which had a narrow, asymmetrical cabin. Only the driver was inside during transit. The other 6 crew members followed the vehicle in a separate transport. This requirement was dictated by safety regulations, as the G-forces inside the cabin during firing reached levels critical to the human body. The gun's aiming mechanism reflected the technical standards of the 1950s. Due to the lack of a rotating turret, horizontal aiming was done by turning the entire vehicle hull, while fine-tuning was handled by an electric drive. Vertical aiming of the barrel was performed by a powerful hydraulic drive, with elevation angles ranging from 12 to 75 degrees. High elevation angles provided the plunging trajectory characteristic of mortars and helped reduce stress on the structure during recoil. The smoothbore section of the gun was manufactured at the Barricade plant in Stalingrad. Foregoing rifling simplified the production process, but it required the use of fin-stabilized ammunition for flight stability. Transporting the barrel, which weighed several tons, from the production site to Leningrad was a complex logistical operation. Moving the equipment by rail to its destination was carried out under strict secrecy, with law enforcement sealing off the tracks at the stations. In the spring of 1957, the main phase of testing began: trials at the proving grounds. The prototype was delivered to a classified facility under the watch of military specialists, industry representatives, and security agents. But the very first shots fired with live ammunition revealed significant design flaws. The recoil exceeded all calculations, reaching 16 feet instead of the allowable 6 to 10 feet. The acoustic impact of the shot was registered miles away. On top of that, the chassis faced critical stress. Despite having been reinforced, the idler wheels broke apart during operation. The hydraulic shock absorbers only partially dampened the recoil energy, which put excessive stress on the structure. Consequently, the gearbox would get ripped from its mounts, bolts and welds would fail, and metal components would warp. After a series of shots, the vehicle inevitably needed repairs. To fix these issues, engineers reinforced key assemblies, changed materials, and reworked the suspension. The tracks could handle the impact, but the road wheels took damage from the shock loads. The lightweight, unarmored hull would twist and bend during firing. The V12-6B engine ran reliably, but the transmission kept failing due to the vibrations and overloads. The calculated rate of fire was 1 shot every 5 minutes, but in practice, the intervals were much longer because the crew had to inspect every system after each volley. The vehicle was 10 feet wide, exceeding standard railway gauges, which made logistics difficult. The 66-foot barrel had a significant overhang, creating obstacles during transport. Its 61-ton weight limited which bridges it could cross, and its off-road performance was poor. Ground pressure of 9.25 pounds per square inch was considered acceptable, but the 137-mile range limited its maneuverability. Despite the challenges, design work continued. In total, 4 units of the Oka self-propelled mortar were assembled at the Kirov plant. Improvements were made to each subsequent unit based on test results, yet they never managed to fully eliminate the issue of structural deformation. The recoil energy from firing a 1,543-pound shell simply exceeded the strength of the chassis, which was adapted from a tank design. The situation demanded either a radically new technical solution or a complete abandonment of the super-heavy artillery concept. On November 7, 1957, Moscow hosted a parade marking the 40th anniversary of the October Revolution. Columns of new military hardware rolled across Red Square. Among the various weapons on display, the large-caliber condensator and Oka systems held a special place. In spite of the technical issues revealed during proving ground tests, the decision was made to show these machines to foreign observers and the press. The sight of this massive machinery rolling across Red Square drew a spirited reaction from the crowd. The gun barrel, nearly 66 feet long and locked at an angle, towered high above the hull. Foreign military specialists viewed the spectacle with skepticism. Some experts suggested that the models on display were merely mock-ups designed for show, believing that building a functional artillery system with those dimensions was physically impossible. Yet, the official announcement during the parade confirmed the combat role of these units and their capability to deliver nuclear warheads. The assessments of the system's actual status turned out to be close to reality, despite some inaccuracies in the details. The artillery complex physically existed and fired shots, but its full combat readiness remained unconfirmed. After the public demonstration, the hardware was returned to the proving grounds, where testing continued at an intensified pace. The clients demanded that the designers fix all technical flaws, a complex engineering challenge. Test firings revealed systemic reliability issues. Cracks were found in the hull's welds, suspension elements failed, and guidance systems broke down due to critical vibrations. The primary objective was to perfect the use of nuclear munitions. The Transformator AR and Transformator D shells were readied for service. The 1,433-pound projectile had a maximum range of 16 miles, with the yield varying depending on the modification. Loading the massive projectile into the breech was a labor-intensive technical operation. It required special crane equipment or a winch. The procedure took a considerable amount of time, even with a well-coordinated crew. The projectile's fins ensured ballistic stability, but further complicated the loading process. The minimum firing range was 2,625 feet, which imposed significant tactical limitations. In the context of nuclear weapons, this created a risk that the launcher itself would be caught in the blast zone. The estimated range for rocket-assisted projectiles was 31 miles, but these munitions were still under development, and their reliability wasn't guaranteed. Vertical elevation angles ranging from 50 to 75 degrees allowed for high-angle fire, characteristic of mortar systems. Communication with command post relied on an R113 radio, though coordinating such massive equipment in combat was considered difficult. The fuel supply provided a range of up to 137 miles on the highway, consuming 25 to 26 gallons an hour. The engine worked under a high load to move the 61-ton structure, and a top speed of 19 miles per hour made the vehicle vulnerable to airstrikes. The sighting equipment included a TPV-51, an S715 angle gauge, and a sight from the ZIS-3 gun, a setup dictated by the requirements for precision aiming. In practice, however, vibrations from firing threw the optical instruments out of alignment. A ground clearance of 18 inches allowed for movement over rough terrain, but due to its significant mass, the machine could sink into soft soil. Simultaneously, tests were being conducted on the condensator system with its 16-inch gun, where operation revealed even more significant technical flaws. The weapon had a rifled barrel and a flat firing trajectory, which caused extremely heavy recoil. After a shot, the rig would roll back 33 to 49 feet, destroying obstacles in its path. Engineers tried to find a balance between power and reliability, but physical limitations created significant difficulties, and both projects hit a dead end. At the same time, the Soviet Union was advancing its missile program. Head of State Nikita Khrushchev prioritized these new types of weapons. Ballistic missiles were considered more promising than massive artillery systems, since they outperformed them in speed, range, and accuracy, and were also easier to transport. The First Secretary doubted the wisdom of developing super-heavy artillery, viewing that class of equipment as obsolete. Despite the leadership's skepticism, modernization work continued through 1958 and 1959. Designers at the Kirov plant and the Kolomna Bureau worked to solve technical problems, changing mounts, reinforcing the frame, and testing various shock absorbers. But the improvements provided only a temporary fix, and subsequent tests revealed new flaws. The metal couldn't withstand the cyclic loads, welds cracked, and fasteners shook loose. On November 7, 1959, the machines were displayed once again at the parade in Moscow. At a public demonstration, 4 self-propelled units were put on display. Foreign specialists meticulously recorded the technical specs, trying to gauge the real combat potential of Soviet weaponry. Intelligence analysts drafted reports and built hypotheses regarding the total number of these machines. Yet the observers had no idea that what had been demonstrated were all the existing prototypes, and technically not a single one was ready for actual combat. Meanwhile, within military circles, debates raged over the feasibility of further developing nuclear artillery. Proponents of continuing the work pointed to the significant funds already spent, the unique design experience, and the gun's calculated power. Opponents, however, countered with technical arguments. The unit was excessively large, unreliable, vulnerable, and showed signs of obsolescence before the testing cycle was even finished. In the spring of 1960, troops began receiving the 2 K-1 Mars tactical missile systems, designated as FROG in the West. These systems were equipped with nuclear warheads and could hit targets at a range of up to 25 miles. Launch preparation took minimal time. Transport was carried out using standard methods, and accuracy exceeded the parameters of artillery systems. Parallel development was underway for the two K-6 lunar complexes and the R-11 Zemlya operational tactical missiles, known abroad as Scud. The evolution of missile technology demonstrated superior tactical and technical characteristics compared to heavy artillery. Ballistic missiles reached supersonic speeds, making them practically impossible to intercept with the air defense systems of that era. Mobile launchers had the ability to quickly change position after firing, avoiding a retaliatory strike, whereas artillery required lengthy topographic surveying and preparation to open fire. The Oka self-propelled guns made their final public appearance on November 7, 1961, during the parade on Red Square. Even as these machines rolled past the reviewing stands, the era of super-heavy artillery was effectively coming to an end. With the dawn of the missile age, the role of delivering nuclear payloads was shifting from large-caliber guns and mortars to guided missiles. By then, it had become clear that the Oka could never be brought up to the necessary level of operational reliability. 3 years of testing, involving hundreds of shots and countless technical fixes, failed to solve the primary design flaw. The recoil energy from firing was simply too much for the tank-based chassis to handle. It would have required either fundamentally new recoil systems or increasing the vehicle's weight to 100 tons or more, which made it impractical to use. At a meeting of the Ministry of Defense's Artillery Directorate, the results of the nuclear artillery program were reviewed. The findings were deemed unsatisfactory. None of the 3 projects, the condensator, the Oka, or the S-103 recoilless gun, ever reached mass production. The S-103 system was destroyed during its 93rd test shot in November 1956, bringing work on that type of recoilless gun to a halt. The condensator faced even more critical recoil issues than the Oka. Economic assessments also confirmed that continuing to develop these artillery systems was not viable. Manufacturing a single unit of the artillery complex required a massive financial investment, comparable to the cost of 10 standard tanks. Operating them demanded qualified personnel, specialized storage conditions, and labor-intensive maintenance. Missile systems offered similar combat effectiveness, but were cheaper and simpler to use, which effectively determined the final choice. In 1960, the USSR Council of Ministers decided to halt all work on the AK and condensator projects. The program to develop super-heavy nuclear artillery was completely shut down. The 4 existing units were to be written off, and further testing was deemed impractical. The significant labor and financial resources spent on development, along with the technical solutions implemented, proved irrelevant in the context of the Soviet Union's updated military doctrine. The project's chief designer, Boris Shaverin, was forced to announce the end of the program. The main reason for stopping work wasn't design flaws, but the physical limitations imposed by the very concept of such high-power artillery. The recoil energy from firing a 16.5-inch round exceeded the technical capabilities of the mobile platforms that existed back then. Afterward, the Design Bureau shifted its focus, applying the experience they gained to create multiple launch rocket systems and anti-tank weapons. The Kirov plant in Leningrad resumed mass production of tanks and heavy machinery, repurposing the assembly lines that had been used for the mortars. For the staff, working on this project remained a significant chapter in the factory's history. The Barricadi plant in Stalingrad continued producing standard caliber barrels, keeping the records and proof of the 66-foot giant's production in its archives. The 4 units that were built met very different fates. 2 of the machines were scrapped and sent to be melted down for metal. The 3rd unit sat for a long time at a closed testing ground, left without proper maintenance. It was decided that the 4th unit would be preserved as a museum exhibit. After the necessary administrative procedures were completed, the self-propelled mortar was transferred to the Military Historical Museum of Artillery, Engineers and Signal Corps in Leningrad. Parallel to these events, the missile program was developing rapidly. The troops began receiving the lunar systems, which had entered mass production at several industrial plants. In total, more than 400 launchers of this type were produced, operating not only in the USSR, but also in Cuba, North Korea, and Poland. The R-17 Elbrus operational tactical missiles, better known internationally as the Scud, became the backbone of Soviet tactical nuclear forces for decades. The United States also made the decision to abandon further development of its atomic Ani artillery system. After a series of demonstration tests and presentations to allies, the project was scrapped for reasons similar to those that determined the fate of the Soviet designs. The 11-inch caliber was deemed insufficient to house a charge of the required power, and increasing it led to the same technical complications the creators of the Soviet high-power systems had faced. As a result, the Western Bloc shifted its focus to creating tactical missile systems like the Honest John and the Lance, which outperformed tube artillery in key parameters. However, the technical expertise gained during the design process was later used by the defense industry. Engineers mastered methods for handling extreme loads, introducing new types of shock absorbers and recoil dampening mechanisms. The experience gained was used in designing heavy mortars of a smaller caliber. In the 1970s, the 9.5-inch 2S4 Tulpan self-propelled mortar entered service and was used during the conflict in Afghanistan and other military operations. This model didn't have the design flaws of its massive predecessor. It was equipped with recoil systems, was lighter, and offered better mobility. A conclusion was also reached regarding the technological limits of tube artillery. It became obvious that there is a threshold of caliber and power beyond which using traditional guns and mortars becomes impractical. Nuclear weapons required different delivery systems, ones that were fast, accurate, and long-range. Missile technology met these requirements, while artillery remained effective only within standard parameters. The only surviving example of the Oka is on display at the Artillery Museum. Visitors examine the massive object, imagining how it would look deployed for combat. The 66-foot barrel, pointing skyward, continues to showcase the sheer scale of the design decades after the project was cancelled. Displayed alongside the self-propelled gun was a mock-up of a 16.5-inch mortar shell, which gave a real sense of the sheer scale of the ammunition used. The development of the Oka system became a prime example of technological evolution, where progress isn't driven just by increasing size and power, but by shifting to entirely new concepts. The designers managed to engineer an artillery piece of exceptional power, yet practical experience showed that this class of weapon was becoming irrelevant in a changing landscape. Priority shifted to missile technology, leaving this vehicle in history as a testament to the era, a period spent searching for the best way to deliver nuclear payloads. The project's lifespan was limited to just 5 years, from the initial decree in 1955 to the cancellation of work in 1960. During that time, unique prototypes were created, and the absolute limits of tube artillery were explored. The engineering data and technical experience gained during testing were later used to design other systems, cementing this machine's status as a significant milestone in the history of military technology.